first. Okay, so let's start. It is our great pleasure to invite Broder to give a talk here. Kähler is a PhD student at the Australia National University and the Beijing International Center for Mathematical Research, and Professor Ben Andrews and Professor Gang Tian. He's interested in curvature characterization of complex analytic and algebra geometric notions of hyperbolicity and non-hyperbolicity. Today, the title of his talk is Recent Developments Concerning the Schwarz Lemma with Applications to the Wu-Yau Theorem. Obviously, an exciting talk is coming. Let's welcome. Okay. Thank you.
Thanks, Chen-Chun. I really appreciate the invitation to give this talk, and hopefully sometime I can come back to Beijing sooner rather than later. So today I'm going to talk about some very recent developments concerning the Schwarz Lemma, and the primary application is going to be to the Wu-Yau Theorem, which we'll get to progressively. This is joint work with three distinct people in three distinct works. Primarily, most of this work that I'm speaking about today is going to be joint with James Stanfield, who's at the University of Queensland. But it builds upon some earlier work that I've done with Kai Tang, who's at Zhejiang. And there are some remnants of some joint work with Simone de Virio, who's at Sapienza. But that's more or less in a different kind of direction with Simone. So let's just start by reminding ourselves of the classical Bochner technique. So if we take Mg to be a compact Riemannian manifold, we take always connected and orientable. We let alpha be some one form on M. Then we can compute the Hodge Laplacian of alpha and compare that with the rough Laplacian given by the Levi-Civita connection. Now, the difference is not zero. It's given by a Ricci curvature term, which acts on the vector field associated to alpha. Moreover, if alpha happens to lie in the kernel of this Hodge Laplacian, namely its harmonic, then up to a factor of 1/2, when we compute the Hodge Laplacian of the norm squared of alpha, we'll get the norm squared of the Levi-Civita connection acting on alpha plus a Ricci curvature term. Now, this is a classical observation of Bochner, which says that if the Ricci curvature happens to be positive, then you'll have a positive strictly subharmonic function on a compact manifold. So by Hodge theory, the first Betti number of your manifold will vanish. This is the essence of the Bochner technique. So we want to look at the Bochner technique or the Bochner formulae in the complex analytic category. So we'll take X omega to be a complex manifold with a Hermitian metric omega. We'll take sigma to be a holomorphic section of a holomorphic vector bundle which resides over X. And we want to compute the complex Laplacian of the norm squared of this holomorphic section. Now, the first thing we need to understand is how to take derivatives. So we need to understand connections on these vector bundles. In the holomorphic category, there's a distinguished connection. So if let's suppose not that E is a holomorphic vector bundle, but just a complex vector bundle, then we can consider a first order complex linear differential operator, D bar, and we'll say that it's a CR operator if it satisfies the following Leibniz rule. So the D bar here without the superscript E is just the ordinary CR operator acting on functions. Now, a priori and in general, this thing will not be too nilpotent in the sense that it won't square to zero in general. But if it does, we refer to it as a holomorphic structure. And the motivation for this jargon comes from the Kobayashi theorem, which says that a complex vector bundle is holomorphic if and only if it admits one of these holomorphic structures. So any holomorphic vector bundle supports one of these distinguished CR operators which squares to 0. Now, if we take D bar E to be a holomorphic structure, we can complete it to a Hermitian connection in the sense that we can find a Hermitian connection on the vector bundle E such that when we look at its 0, 1 part, it coincides with this holomorphic structure. So if E happens to be the tangent bundle, for instance, this is commonly referred to as the Chern connection and is the distinguished connection on a holomorphic vector bundle. So if we look at the Bochner formula in this case, it's particularly simple to derive because if I act on a holomorphic section by the 0, 1 part of the connection, it will vanish because it coincides with this CR operator. And so we end up with the following nice looking Bochner formula, which says that the complex Laplacian of a norm squared of a holomorphic section is the norm squared of the Chern connection acting on sigma minus the curvature form acting after being paired with sigma. Okay, so an important application, at least for what I've been focusing on, is to the Schwarz lemma. So if we take F to be a holomorphic map between complex manifolds, we can think of the differential of F as a section of the cotangent bundle of X, but taking values in the pullback of the tangent bundle of Y. So if we take sigma to be dF, and we take E to be the tangent bundle of X twisted with the pullback of the tangent bundle of Y, the Bochner formula takes the following form. So to understand how to compute the Laplacian of the norm squared of the differential, we need to understand how this curvature behaves. So this follows quite straightforwardly from the algebraic properties of the curvature, namely that it will split additively under tensor products. So the curvature of the tensor product is the sum of the curvature of the cotangent bundle with the pullback of the tangent. If we take the corresponding dual bundles, it will invert additively. So the curvature of the cotangent will be minus the curvature of the tangent. And finally, it commutes with the pullback in the sense that the curvature of the pullback is the pullback of the curvature. Now, when we feed this into the Bochner technique, we'll see that since we're going to be taking the Laplacian with respect to a metric on X, there'll be a trace occurring, which will trace over this curvature, but have negligible impact on here. What do I mean by that? I mean, if we look at the Bochner formula spelled out in this case, we'll see that the Laplacian of the norm squared of the differential is the norm squared of the Chern connection acting on dF. Because of the trace, we'll get a Ricci curvature of the source appearing, but we'll have a full curvature of the target appearing. So it's probably more enlightening to view this in local coordinates. So if we write this out, we see that we get the Laplacian of the norm squared of the differential to be a Ricci curvature term, which is given by contracting over the first two indices. This will turn out to be an important observation. But there's no trace affecting the curvature because it's obviously a different curvature on the target. So if we want to carry out the standard Bochner technique, we'd need a lower bound on the Ricci curvature and a preferably negative upper bound on the curvature of this target metric. So let me also just mention that by Fi alpha, I mean the ith partial derivative of the alphath component of F. Okay. So to handle the target curvature term, so we know that the source curvature term is handled by the Ricci curvature. It's the target curvature we need to worry about. There's an old observation of Royden, which he observed in the 80s, which was if the metric on the target happens to be Kähler. So for us, that's really going to mean that the torsion of the Chern connection vanishes. So in particular, the curvature tensor has all the symmetries of the Riemannian curvature tensor. Then we can control this target curvature term by the holomorphic sectional curvature. And just to remind everyone, if we take, for instance, omega to be a Kähler metric with an underlying complex structure J, then the holomorphic sectional curvature is given by the restriction of the sectional curvature to the J invariant two planes. So the two planes of the form U, JU. In terms of the curvature tensor itself, so if R denotes the Chern curvature tensor, the holomorphic sectional curvature in the direction of the 1, 0 tangent vector V is just R acting on V, V bar, V, V bar. So just to give some insight into the holomorphic sectional curvature, it's arguably the most natural of the curvatures to study within complex geometry itself. Namely, it's an elementary consequence of the Schwarz Lemma that if you have a complex manifold with a metric of negative holomorphic sectional curvature, then it's Brody hyperbolic. In other words, every entire curve, so a holomorphic map from the complex plane into the complex manifold X is constant. If X happens to be compact, this is equivalent to what's called Kobayashi hyperbolicity. And I'll more or less use these words interchangeably since I'll be assuming compactness for the most part. On the other hand, there's a more recent result of Yang Xiaokui, which says that if you have a compact Kähler manifold with a Kähler metric of positive holomorphic sectional curvature, then the manifold is rationally connected. Namely, any 2 points lie in the image of a rational curve. So this gives us some intuition for what the holomorphic sectional curvature measures. It measures the value distribution of holomorphic curves within your manifold. If it's negative, there are none of them, but if it's positive, they exist in abundance. Now, the argument that Royden gives to control the target curvature term in the Schwarz lemma by the holomorphic sectional curvature hinges upon the following polarization argument. So if we let S be a symmetric bi-Hermitian form, which we understand to be symmetric in the first and third arguments, and when taking conjugates, we see that we have an inversion in the first and second arguments with appropriate of this symmetric bi-Hermitian form when you insert the same argument, the same vector into each of the 4 arguments, and you've controlled that from above by a negative constant or non-positive constant. Curvature. And so it suffices to control the target curvature by means of the holomorphic sectional curvature. So as a consequence, we have the following result. So if we take F to be a holomorphic map between Kähler manifolds, we suppose that the Ricci curvature of the source metric is bounded below by a negative constant. We suppose that the holomorphic sectional curvature of the target is bounded above by a negative constant. then if we look at the Laplacian of the trace of the pullback, which is equivalent to the Laplacian of the norm squared of the differential, then we have the following pointwise inequality. In particular, if X happens to be compact, then we have the following bound by the maximum principle. So for instance, if C1 was positive, so if this Ricci curvature was positive and the holomorphic sectional curvature was negative, you wouldn't have any non-constant holomorphic maps. So an important application is what's referred to as the Wu-Yau Theorem. It's due to a number of people, and I haven't listed all the contributions here. I've omitted any consideration of quasi-negativity, or there's some intermediate results concerning Picard number 1 and so forth. But it's originally due to Wong for surfaces. The kind of beginning of the recent developments began with a paper of Haier, Liu, and Wong for projective threefolds. The kind of general case was achieved by Wu-Yau, at least in the projective case. And Tasati Yang later observed that you could drop the projective assumption. So the theorem states that if we have a compact Kähler manifold, negative holomorphic sectional curvature, then the canonical bundle is ample. So in particular, the manifold is projective. A negative holomorphic sectional curvature, then by perturbing the metric within the cohomology class, so consider omega phi, then one can choose phi such that the Ricci curve is negative. And it's a question of de Virio as to whether one in general has to change the metric, or whether one can understand when one has to change the metric. So understanding which conditions can we take phi to be 0, and are there conditions in which we have to, which we know that we have to take phi to be something that is non-zero. That is completely unknown from what I understand. Okay, so this fits more generally into what's really called the Kobayashi conjecture. So the Wu-Yau theorem is an important step towards this more general conjecture, which asserts that if we have a compact Kobayashi hyperbolic manifold, so you just have a compact complex manifold in which all holomorphic curves from the complex plane into X are constant, then Kx is ample. So this is a relaxation in a number of ways. Metric with negative holomorphic sectional curvature. It was conjectured to be equivalent for a long time, but in 1997, Desmailly constructed an example of a projective Kobayashi hyperbolic surface, essentially a high genus vibration, a high genus curve criterion. Then you can produce an example which is Kobayashi hyperbolic, but doesn't have such a negatively curved metric. So I should also remark that, to my knowledge, Kobayashi only conjectured this for compact Kähler manifolds, but a number of people have been working on it, trying to get it in full generality without the Kähler assumption. Okay, so let me just indicate why the Wu-Yau theorem is of particular interest outside of this conjecture. The surprising thing is that the holomorphic sectional curvature and the Ricci curvature, at least for a Kähler metric, occupy very similar strata on the curvature hierarchy. What I mean by this is that they're both dominated by the holomorphic bisectional curvature, is one of the strongest constraints in complex geometry. And they both dominate the scalar curvature, what their relation is. So for instance, we have the following example of Hermitian. So we can consider the nth Hertzebruch surface. So these are projective bundles, which are P1 bundles over P1. And Hermitian showed that all Hertzebruch surfaces admit Kähler metrics of positive holomorphic sectional curvature. But if we take n to be bigger than 1, the first Chern class will no longer be positive. And so they can't admit Kähler metrics of positive Ricci curvature. So in particular, we see that the holomorphic sectional curvature being positive doesn't imply that Ricci curvature has to be positive. The holomorphic sectional curvature is not strong enough to dominate the Ricci curvature. On the other hand, if we consider something like a degree D Fermat hypersurface sitting inside Pn, then if we take D to be greater than or equal to n plus 2, the adjunction formula will tell you that the canonical bundle is ample. And so in particular, by Orban-Yau, there's a Kähler-Einstein metric of negative Ricci curvature. But by results in algebraic geometry, we know that X. And so in particular, that would violate this Brody hyperbolicity criterion that we saw before. And so there can't be a metric of negative holomorphic sectional curvature. So this example shows that negative Ricci does not imply negative holomorphic sectional curvature. This makes the Wu-Yau theorem particularly curious. Okay, so let's just give a brief sketch of the Wu-Yau theorem. So to do this, let me just let's remind ourselves that a cohomology class in the second de Rham cohomology is said to be a Kähler class if it can be represented by a Kähler form. So we look at the associated 1-1 form, that's going to be closed if it's Kähler. And so we'll define a de Rham cohomology class. Kähler class is exactly one which can be represented by a Kähler form. If we look at the set of all such things, these form what's called the Kähler cone, which is an open convex cone in the finite dimensional vector space H11XR, which sits inside H2. And the cohomology classes which reside on the boundary of the Kähler cone are referred to as NEF classes, so numerically effective classes. So the key step is to really show that the canonical bundle is NEF. To go from NEF to ample is more or less the same argument, but getting NEF is the challenge. So standard argument is as follows. We proceed by contradiction and suppose that this is not the case. And that'll give you some epsilon 0 such that if you scale the Kähler class represented by your Kähler metric of negative holomorphic sectional curvature, omega g, by epsilon 0, and then subtract the first Chern class of the anti-canonical bundle, then by rearranging the definition of kx not being NEF, you'll see that that's a NEF class, but not Kähler. So it lies on the boundary of the Kähler cone, but not in the interior. Add an epsilon times the Kähler class to go from a NEF to a Kähler class. And so this is represented by a Kähler metric. So after adding I to d bar of phi epsilon, we have a Kähler metric epsilon plus epsilon 0 omega g minus reach omega g plus I to d bar phi epsilon. Noting here that the first Chern class of the anticanonical bundle is represented by the Ricci curvature of omega g. Now, by the Wu-Yau theorem, we can find a smooth function psi epsilon such that this metric omega epsilon is positive definite and satisfies the following Monge-Ampere equation. So we have this equation of volume forms with the ratio being e to the u epsilon, where u epsilon is phi epsilon plus psi epsilon. Now the Monge-Ampere equation gives you control of the Ricci curvatures. So if you take I to d bar log of both sides, we get that the Ricci curvature of omega epsilon is Ricci omega g minus I to d bar u epsilon. But then if we just rearrange this definition, we see that this is just minus omega epsilon plus epsilon epsilon 0 omega g. So we have a Ricci lower bound on the metric omega epsilon. We have a negative holomorphic sectional curvature bound. Well, we have negative holomorphic sectional curvature of omega g. So by Royden-Schwarz lemma, we get an estimate on the trace. Moreover, this is uniform in epsilon for epsilon small. So what we want to do is we want to contradict the fact that this cohomology class up here is Neff but not Kähler. The idea is to bootstrap from this C2 estimate here, allowing epsilon to go to 0, extracting a smooth limit, which will be a Kähler metric, violating this here. So if we look at the point where u epsilon attains its maximum, we'd have I to d bar of u epsilon being less than or equal to 0. And that will give us that this multiple of the metric minus its Ricci curvature will be positive at that point. And so we can bound the exponential of the supremum of u epsilon by the corresponding volume forms. So we now have an estimate on trace omega epsilon omega g and a bound on the ratio of the volume forms, which are uniform independent of epsilon. And so by the standard AMG inequality, we have a bound on the reverse trace. So in particular, we get two-sided bounds on omega epsilon, which are independent of epsilon, and we have these this uniform constant C. So now by standard bootstrapping, we can get to all higher order estimates. These estimates will depend on K, but they won't depend on epsilon. Now by the standard techniques, you apply a Zeller-Ascoli to extract some subsequence, call it epsilon I tending to 0, such that omega epsilon I converges smoothly to a Kähler metric omega 0 that will satisfy at the level of cohomology classes that it represents, the cohomology class it represents will be given by epsilon 0 omega g minus the first Chern class of the anticanonical bundle. But this was the cohomology class that we assumed was Neff but not Kähler. So we have a direct contradiction. So given that the canonical bundle is Neff, we can apply more or less the same argument. So this time we'll have an epsilon positive. We can find a smooth function u epsilon such that this omega epsilon is positive definite, solving this Monge-Ampere. Same argument again shows that we can extract a convergent subsequence converging to this metric omega u, which is given by minus the Ricci curvature of omega g, I to d bar u. That will be a positive definite Kähler metric satisfying this Monge-Ampere. But if we take I to d bar log of both sides, then we'd get the Ricci curvature of omega u is the Ricci curvature of omega g minus I to d bar u. But that's precisely minus omega u. So we've constructed a Kähler-Einstein metric with negative scalar curvature. And so in particular, it has to be ample. So if we want to extend this towards the more general Kobayashi conjecture, the hinge point is the Schwarz lemma. The Schwarz lemma is the real obstruction here. So the first thing to be concerned with is that the Monge-Ampere equation only controls the first Chern-Ricci curvature. This is the contraction over the third and fourth indices, not the first two indices. Now, this is not a problem in the Kähler case, since you have the symmetries of the Riemannian curvature tensor, but a Hermitian metric will certainly not satisfy this in general. The problem is that in the Schwarz lemma, the second Chern-Ricci curvature appears, namely you have a contraction over the first two indices. The second and more concerning problem of late has been that the Royden polarization argument forces you to be able to interchange the first and third entries of the curvature tensor. That's one of these criterion that was used in Royden's argument. And a non-Kähler metric in general will certainly not satisfy such symmetries. So the Schwarz lemma in the Hermitian category is obstructed by the Ricci curvature not being the one that we can control by a Monge-Ampere, and the target curvature is not controlled a priori by the holomorphic sectional curvature because Royden's argument doesn't go through. So to understand this target curvature term, we'll fix a point, choose a frame in which the metrics are Euclidean, and write the matrix corresponding to df in terms of its principal values, lambda I. And when you do this, you see that the target curvature term which appears in the Schwarz lemma is given by a weighted sum of these quadratic components of the curvature, weighted by the squares of the principal values of this differential of f. Now, this was observed by Yang and Zheng in around 2017, and they defined the following. So they consider for an arbitrary Hermitian manifold, consider the real bisectional curvature to be exactly this term which appears in the Schwarz lemma. So you take a real weighted linear combination of these quadratic components weighted by real numbers, which I've written as V here, but they correspond to the squares of the principal values of the differential. So if the metric is Kähler, the real bisectional curvature is comparable to the holomorphic sectional in the sense that they dominate one another. If one of them is positive, the other is positive. If one is negative, the other is negative, and so forth. They have the same sign. For a general Hermitian metric, however, the real bisectional curvature strictly dominates the holomorphic sectional, and it also dominates the scalar curvatures. So at the moment, it's not known whether the holomorphic sectional curvature dominates the scalar curvature in the general Hermitian case, but this is known to be true for the real bisectional curvature. On the other hand, the real bisectional curvature is not so strong in that it doesn't control the Ricci curvatures. So it's thought of as a minor or slight strengthening of the holomorphic sectional curvature and is motivated almost exclusively by the Schwarz lemma calculation that we just did. I should add that when we say that the real bisectional curvature is positive or negative, this is assumed for all frames. So this is another problem with the current state of affairs, is that you have to assume this condition on all frames, which is obviously not natural. Okay, so more or less applying all the previous arguments, Yang and Zheng prove the following. So they have that if we consider a holomorphic map between Hermitian manifolds, assume that its Ricci curvature is bounded below, its second Chern-Ricci, I should emphasize, is bounded below. You assume the real bisectional curvature of the target manifold is bounded above by a non-positive constant, and you end up with the following pointwise inequality on the Laplacian of the log of the norm squared of the differential. So in particular, if X is compact, applying the maximum principle gives you the following estimate. Okay. So more or less, the previous argument that we gave for the Wu-Yau theorem can be applied almost verbatim, just transferring the version of the Schwarz lemma that we have now. And this led to Yang Zheng establishing the following corollary. So if we have a compact Kähler manifold, negative real bisectional curvature, then the canonical bundle is ample. It's clear that you just proceed with the same argument, replace Royden's Schwarz lemma with this Hermitian Schwarz lemma due to Yang and Zheng. Now, we want to extend this in the Hermitian category. You want to extend the Schwarz lemma as far as you can, because that's the key abstraction. The natural thing to do in Hermitian geometry is, if you can do it for the Chern connection, you want to do it for all Gauduchon connections. So Gauduchon introduced this one parameter family of Hermitian connections, which are given by a convex combination of the Chern connection with the Lechnerowitz connection. So this is, the Lechnerowitz connection is given by taking your Levi-Civita connection, which resides on the real tangent bundle, complexifying it and projecting it orthogonally onto the 1,0 tangent bundle. So this one parameter family of connections passes through the Bismuth connection, which is the unique Hermitian connection with totally skew symmetric torsion, and passes through a number of other distinguished connections. And it's very natural to try to get the Schwarz lemma, which we know for the Chern connection, so if we recall how we constructed the Schwarz lemma, what we did is we started with the Bochner formula, and we applied the Bochner formula to the section DF, which was a section of the cotangent bundle tensored with the pullback of the tangent bundle. So if we want to extend the Schwarz lemma, the first obstruction is this Bochner formula. So we want to extend the Bochner formula beyond the Chern connection and get this formula for any Hermitian connection. So this actually turns out to be not too difficult. And that's the first novel result. So if we let E be a holomorphic vector bundle over a Hermitian manifold X, we'll take nabla to be a Hermitian connection on E. So we don't assume that its 0,1 part is given by the holomorphic structure. Then for any holomorphic section sigma, the Laplacian of the norm squared of sigma is given by the following 4 terms. So the first term and the last term are what appear in the classical analytic Bochner formula. This term appears because this is no longer the holomorphic structure, so it's not necessarily 0, but it's harmless because it's a norm squared, so it's going to be positive. the key observation or the key point to take away is not that you have this kind of nice formula now, it's that you now only have to compute this second order divergence term. So you've reduced this immense task of computing these two derivatives, which unfortunately in the non-Kähler case, you don't have nice coordinates to work with in general. So the computations become formidable very, very quickly. So the point of this Bochner formula is really that you can now reduce the computation to this. Now, the end application is going to be to apply it to sections associated to bundles, which are or sections of bundles which are associated to the tangent bundle. So for instance, with the Schwarz lemma, we want to apply it with the cotangent bundle tensored with the pullback of the tangent. And the idea is you want to extend the general framework, these general abstract Bochner formulae, as far as possible before you descend into the chaos of the coordinate calculations. Because, like I was saying before, the calculations become extremely formidable. So you want to stay kind of as far back as you can for as long as you can, and then delve into the chaos of analyzing the constituent terms. So we want to push that Bochner formula from the previous slide a little further, especially considering we want to understand how torsion is playing a role. And we do this by introducing the following probably poorly termed definition. So we refer to an endomorphism valued 0,1 form as the CR torsion if it is given by this difference. So it's measuring the deviation from the Chern connection. So in particular, if A is 0, then your Hermitian connection would be the Chern connection. Now, this may seem a bit unnecessary, but it turns out to be a fruitful computational tool. For instance, if we formulate the previous Bochner formula in terms of this CR torsion, we end up with the following. So if we take E to be a Hermitian vector bundle, which is some tensor bundle associated with of the CR torsion in the following way. So we see that we get a covariant derivative of the CR torsion. We get another term which involves a covariant derivative of the section. And then we get this third term, which will be further terms involving torsion. Now, of course, this is still very abstract, but this look at any Hermitian connection. It doesn't have to be Gauduchon yet. It's going to be any Hermitian connection on the tangent bundle of X and the tangent bundle of Y. Then the Laplacian of the norm squared of df satisfies the following more intimidating formula. So the point here is that the first line is the standard Schwarz lemma, the terms that appear in the standard Schwarz lemma calculation for the Chern connection. The second two lines are these will, after applying iterations of the Bianchi identity, will give you Ricci curvature terms, together with some other real bisectional curvature terms, which we'll see in a moment, particularly concerning these two terms which appear in red, because these are covariant derivatives of the map F itself. And you don't want to assume conditions on the map. You only want to assume conditions on the curvatures. This term is harmless, more or less. But this term is particularly useful because if we assumed, for instance, that the metric was balanced, this term vanishes. So that's particularly fruitful. So, okay, so if we now take the connections to be Gauduchon, and moreover, we consider the same Gauduchon parameter. So a priori, there's no reason to consider the same Gauduchon parameter. You could take the T Gauduchon connection on the source those terms will become imaginary. So if you take the real part, it's going to vanish. Now, as I said, with the covariant derivatives of the torsion, if you bash out the first Bianchi identity, which is certainly a non-trivial task, it does take quite a bit of work, we end up with these Ricci curvature terms coming from the source. We end up with still torsion terms on the source here. And we end up with some real bisectional curvature terms on the target, and then these other torsion terms on the target as well. Now, of course, this is much more complicated. This is why I can't state an abundance of theorems, because it does take some time to analyze all these terms. But the exciting part is that you see all these Ricci curvature terms appearing with coefficient functions which you can manipulate as functions of t. So if you had, for instance, a certain bound, you could attempt to manipulate the t in such a way that it is more optimal for this type of calculation. Maybe there's another curvature which you can't control, which you can try to get that corresponding term to vanish. So that's one of the really exciting parts of this recent developments. So, for instance, if we were to assume, just to simplify the formula, that the target, or the source metric, sorry, was Kähler, then all those torsion terms coming from the source would vanish, and we would end up with just a Ricci curvature contribution from the source. Now we have a real bisectional curvature term with an altered real bisectional curvature term. So the definition of this altered real bisectional curvature term is just the same thing, but we're taking the indices are changed slightly. So I take I k bar ki bar instead of I bar kk bar. The holomorphic sectional curvature is given by a sum of these. So that's particularly fruitful, especially since both of them are appearing here. And moreover, the torsion terms have a sign. And so in particular, we can manipulate the coefficients. Okay, so the next observation in this string of ideas was this monotonicity theorem for the holomorphic section. Holomorphic sectional curvature with respect to the T Gauduchon connection be denoted as follows. Then one can show that it's maximized when T equals 1. And this corresponds to the holomorphic sectional curvature of the Chern connection. So if you assume that the holomorphic sectional curvature of the Chern connection is negative, then the holomorphic sectional curvature of all the Gauduchon connections is also negative. Assumption you could place. Now, in light of this result, one could hope that by assuming negative holomorphic sectional curvature of the Chern connection, since those are not appearing for the churn, those are appearing for the T Gauduchon connection. So you could try to manipulate the coefficients and so forth, given that the real bisectional is only a minor strengthening of the holomorphic sectional curvature. This turns out to be the case. So if you take the Gauduchon parameter to be within this range, then one can show that the holomorphic sectional curvature being negative implies that this term, which is exactly what appears in the Schwarz lemma, turns out to be positive. So the next thing to check is that all the other torsion coefficient functions are positive in this range, and this also turns out to be the case. So what you end up getting is the following result, which is that you can extend the Schwarz lemma. So you assume Ricci lower bound on the source manifold, assume the source manifold is Kähler, and assume not that the real bisectional curvature is negative, but that the holomorphic sectional curvature is negative. Then you can proceed with the Schwarz lemma as before and get the Schwarz lemma estimate. So what's kind of exciting about this is we're only assuming the standard assumptions. We're not assuming anything about Gauduchon connections. But to get the improved estimate, you need to pass to the Gauduchon connections. You need to kind of extend to all values of T, prove the estimate there, and then reduce back. It's kind of a novelty that I wouldn't have expected until we kind of really got into the dirt of these calculations. Now, as a consequence of this refined Schwarz lemma, we see that we have the refined Wu-Yau theorem. So if we have a compact Kähler manifold, which supports a Hermitian metric of negative holomorphic sectional curvature, then the canonical bundle is ample. So we've improved the real bisectional curvature assumption to a natural holomorphic sectional curvature assumption. I should also add that this is really just one result of many more things that we're hoping to get out of this. It's just that as we saw before, the Schwarz lemma that we get now is extremely technical. And so if you're going to prove anything, you really have to kind of analyze a bunch of terms and check that certain values of T work and that they all kind of give you what you want. So this is really active research at the present time, but it's also very exciting. So we don't have to, in particular, assume Kähler source. You could get quite far with a balanced metric on the source, for instance. And we're hoping to get it in full generality. Okay, so in light of this monotonicity theorem for the holomorphic sectional curvature, it's natural to ask the following question. So Desmailly showed that there are compact Kobayashi hyperbolic manifolds which don't admit metrics of negative holomorphic sectional curvature. But the monotonicity theorem asserts that the negative holomorphic sectional curvature for the Chern connection is the strongest constraint. So it's natural to ask whether compact Kobayashi hyperbolic manifolds can be characterized by the negativity of the Gauduchon holomorphic sectional curvature for some range of T. That would be a rather interesting thing to know. Similarly, Yang was able to show that if a compact Kähler manifold had a metric of positive holomorphic sectional curvature, then it's rationally connected. But that's false for a general complex manifold with a Hermitian metric. For instance, a Hopf surface has a metric of positive holomorphic sectional curvature. But since the universal cover is C2 minus the origin, any rational curve would lift to a holomorphic map on the universal cover, and there are no such maps from P1 into C2. So there's no rational curves on the Hopf surface. but perhaps there's a certain range of T such that positive T Gauduchon holomorphic sectional curvature implies rationally connectedness. These are two aspects of the story that would be particularly interesting to understand. And at this point, I think I'll stop here. Thank you.
Okay, thanks so much. This is a very nice talk. Thank you. Okay, so any questions or comments? I have a question. Please scroll up. I remember it's the last 2 pages, and you and James proved. Yes, here. Okay. Oh yes. For this theorem, is that possible? Because I think it is very interesting if we can remove the Kähler assumption. So is that possible in lower dimension? Okay. For example, say if 2-dimensional, is that possible to remove this Kähler assumptions? I don't know. Maybe
so in the Kähler, so for surfaces, you can just go by classification.
I see.
You can actually, I think the Kobayashi conjecture is true for surfaces just by classification arguments.
I see.
Okay, if it's Kobayashi hyperbolic, it has to be ample. There are no class 7, for instance, which could be Kobayashi hyperbolic. We're working on removing the Kähler assumption.
Okay,
so
I see.
The key point for the Kähler assumption is to be able to use the Monge-Ampere equations. There's some developments by Tessati, Weinkow, and
I see.
For the general complex Monge-Ampere. But you need to, so one of the key
for the
points
constant?
Here is you can, it's the fact that the Ricci curvature, you need to be able to control the first Chern Ricci. Well, in the Schwarz lemma, the second Chern Ricci appears. You want to control that by the first Chern Ricci.
I see, that's the point, yeah.
That's one of the key points, but it's also delicate because the structure of the argument resides upon these cohomology arguments, and you don't have that. So you really have to spell everything out in terms of the Monge-Amperes.
I see. Okay.
What I'm saying is I think it's possible, but I think it's subtle. I think it's you have to be delicate. You can't just wipe out.
Yes, I agree. Removing the Kähler assumption completely is very difficult. So maybe just a very naive idea. Is that possible? Say, okay, under pluriclosed condition, or say, okay, acidental Kähler some weak assumption compared to just very naive idea.
We get a lot of traction in the balanced case.
Oh, balanced case, yeah.
But we think we can get it. Well, we have an idea on how to get it in general. But there is a playoff between this pluriclosed and balanced. You can't assume both, because if you assume both, it's Kähler. But there is a curious relationship which appears for pluriclosed metrics between the first and second Ricci curvatures.
I see.
But this is still very, this was, James and I were talking about this yesterday. So it's still very, very active.
Very interesting topic. Yes, very interesting question. Yes.
Yes, it's very, so it's a beautiful problem. It's a beautiful problem.
Of course, yeah. Okay, any other questions or comments? Okay, if no questions or no comments, let's thank the speaker again. Thanks so much. This is a very nice talk. Thank you. Yeah.